Hi students, welcome back to the online video lectures on DSP. So this would be the 7th module on discrete Fourier series and discrete Fourier transform. In this video, we would be discussing about the properties of the discrete Fourier transform. So if you have comfortably understood earlier the properties of discrete Fourier series, in a way they will be very similar to DFT properties will be very similar to DFS, except that there, if you, for example, given here you have just one period of a signal, or it's equivalent to when you compare DFS versus DFT. So this is DFT is equivalent to finding out the Fourier transform of one period of your periodic signal. So usually most of the properties, if you construct a periodic signal out of your given finite length signal and then apply the properties of DFS, and then just remain at the end, if you retain just one period of the resulting sequence, in most of the cases you will get equivalent results compared to directly applying these properties that we are going to discuss here. Okay, with that, let me start going through it. Let me move on to desktop sharing mode, and let me move to notebook mode. Okay, so let's, as usual, we will first discuss about the linearity property. Okay, recollect the linearity property we did in case of DFS. If one of the periodic signal is having a periodicity of n1, another is having an n2, LCM of n1 and n2 was giving you the periodicity that you would use while combining two different sequences. So here that's slightly different. Assume that you have two signals, let's say some x1 of n, something like, yeah, let me draw something. Okay, assume that is my x1 of n starting from 0 to n1 minus 1, and this is the x1 of n. This is varying n. You could see here the length L1 of that signal is n1. Okay, and take another signal. Okay, of length, let's say it's starting from 0 ending with n2 minus 1. Let us call this as x2 of n, and let the length of the signal be n2. Okay, now any idea on which point DFT we have to compute here? Well, all you need to do is your length n point DFT, your n has to be the maximum of n1 and n2. That's what you would use while applying this property. So assume that your n1 is, for let's say 4 and n2 is 6. All you do is, for the first sequence x1 of n, you will append couple of zeros and then you proceed and then you compute. So then if you do that, and here when I am saying DFT, that's in all the cases that's n point DFT. Okay, now what could I say with this property? If x1 of n, the DFT is x1 of k, and for x2 of n, as I mentioned, these two are of same point DFT. That's the number of points being equal to maximum of n1 and n2. Then what I could say here, if I am going to find out the n point DFT for a signal which is a times x1 of n plus b times x2 of n, the DFT of that would be equal to a times x1 of k plus b times x2 of k. That's as far as the linearity property is concerned. So second one, another very important property. Okay, let me first refer to it as circular shift, then we will come back to what it means. Okay, circular shift of a discrete time sequence. Okay, that's what we are going to take a look at here, of a discrete time sequence. It would be easier to understand this if we first, let me write it for DFS, what we did for a, in case of a shifting of a signal. Suppose if for a periodic signal x tilde of n, the DFS is capital X tilde of k, then if I had x tilde of n minus m shifted by m, the DFS is then in that case e power minus j, well, this m less than the capital T, right, that's also even a positive number, minus j 2 pi by n times k times m, okay, into x tilde of k. See, what it would happen is, we also, if you recollect the way we made the shifting, you could do, now what is it that we want to take a look at here is, suppose x of n, the DFT is given as capital X of k, right, and suppose here I have similar stuff, 2 pi by n times k times m times x of k. Let me call this as x1 of n. So what is that value is the question. So it's not difficult to make a guess here. You construct from DFT to DFS, okay, periodic thing, repeating that. So that should give you then x tilde of n minus 1. So from earlier discussions in the previous classes, it should be already clear to you that this x1 of n would in fact be equivalent to x of n minus m modulo n, if you are doing the n point DFT. That's all. So even we applied this, if you recollect, in case of DFS, where we are doing all manipulations based on a single period of that signal. So this, let me, if you want, yeah, that's fine, I think I will just leave it that way. Okay, this x1 of n, so if you want, yeah, better let me write it here itself. Okay, this would be equivalent to x of n minus m modulo n. Okay, let's solve one example here, one example problem here. Let's say I have a sequence of 1, 2, 3, okay, 4. I'm reducing the scale a bit, then what it should have been. Okay, fine. So n, this is n, 0, 1, 2, 3, 4. Okay, this is my, let's say, my x of n. Okay, what I would like you to draw here is, for example, I am doing here on the right hand side, so e power, I want the DFT to be e power minus 2 pi by what shall we call here, n value could be, for example, 5 here. Okay, so 2 pi by 5 into I want to shift, have a shift there by 2, factor 2. Okay, so let me write it as 2k into the x of k, right? And I'd like to know what shifted sequence would give this, right? You have here m to be 2, so what would happen here? Your x1 of n, okay, if I call this as x1 of k, the x1 of n would be equivalent to x of n minus 2 modulo 5. is it not? Right. So let me draw that out now. 0, 1, 2, 3, 4. X of 0, for example, I want that minus 2. So another important thing I want you to pay attention is, for example, when you have let k be a positive, so maybe better I would just simply, yeah. So for example, if I have x of minus k modulo n, where this k is a positive value, that means for a negative value you are trying to find out the modulo operation. So that's in fact is equivalent to, in the circular shift, is equivalent to n minus k. Okay, this is again, you could go back to the previous lectures and verify this out. Okay, or from periodic signals also you could verify that out. Okay, yeah, with that let me come back here. So x of for example x1 of 0 is equivalent to x of minus 2 modulo 5, that's equal to x of 5 minus 2, is it not? That's equal to x of 3, right? X of 3 was 4, that would, what would come here? This is 4 here. Similarly, x1 of 1 is equal to x of minus 1 modulo 5, that's equal to 5 minus 1, x of 4, x of 4 equal to 5. So this is 5. Then x1 of 2 is equal to x of 2 minus 2, 0, right? 0 modulo 5 is of course 0, x of 0, right? So that's x of 0. X of 0 is 1. I would get here 1. And x of, similarly, x1 of 3 is equal to x of 3 minus 2, 1 modulo 5, right? So that would give you 1 only. So that's x of 1, which was equivalent to 2. You do the same thing, this would be equal to 3. Okay, this would be your x2, yeah, I'm calling it as x1 of n. So this is what you get here, right? Let me simplify things for you. While this is what you initially work it out in this manner, but then also pay attention here how quickly you could draw this out. One way you could think of is you just keep one copy, periodic copy here, one periodic copy there, okay, with periodicity of capital N. You shift then the whole thing and see whatever is there from 0 to 4. That's one way of interpreting things. Another way of interpreting things is you need to shift it by 2. So when you do that, you first do the shift there. For example, alternative way of drawing it, okay, is, for example, you shift this whole thing by 2, correct? You want n minus 2 modulo 5 if you want it. You first shift it by 2. That means what do I get there? Right, 0, 1, 2, 3, 4, 5, 6. Okay, this is starting from 0 to 4. You shift it by the whole thing by 2. So then whatever is 0 would now the whole thing would start from 2. Okay, so here I would get 1, 2, 3, 4, 5, right? And you already so this is what you want to in the circularly. So had it been periodic function, it might be the other side would come, but here what you do is anything that is there beyond your n, you just this is shifting towards that, you bring it here. That means you just import that here. So that would come here as 4, for example, here. So that would give me, okay, let me draw it in blue only, so that we easy to follow. This is 4 and I would get here 5, and you drop that out. This, okay, this is your n, this is your x1 of n. So this is another alternative way 1. Okay, this is if you consider the first one. So 4 5 1 2 3. Okay, 4 5 1 2 3. As I mentioned, let me also, for the sake of completion, this is not recommended, okay, but to begin with, just you have this interpretation as well, where you originally had this one 0 1 2 3 4, right, 1 2 3 4 5, okay, 1 2 3 4 5. This is your n. Okay, now you construct a periodic signal out of it, okay, with whatever is your n point DFT is 5 point DFT. So you start repeating it from here. So let me draw it with a different color here. Okay, this is 1 2 3 4 5, okay, and you keep the copies on the other side also. So once you keep it, for example, here, then 5 would come here, 5 4 3 2 1, okay, and of course this would be minus 1 minus 2 minus 3 minus 4 minus 5, and this would be 5 6 7 8 9, and of course on both sides you could have it, and you need to shift it by 2. For example, if you are doing the earlier operation in case of DFS, you shift it by 2, right, to the right. So what will you get then if you are shifting it? So this is 4, this is 5, that's what would come here. This is, for example, what would happen here? So when you are shifting that, 4 would come here, right, and 5 would come here at 2, and of course then this 1 2 and 3, this would be there. This is 0 1 2 3 4. You are shifting whole thing here in this direction, okay, by 2. So that's another way you could interpret that, and this would give you your x1 of n. If you want, you could first draw x1 tilde of n, the whole thing, and then take one period of that, and that would give you x1 of n. Okay, so if you want, let me let me, maybe since we have drawn it, let me just draw this 4 5 3 2 and 1 here. Okay, once you shift it, okay, here anyway there is 4 5, okay, and of course this is 1 2 3 4 5 6 0 minus 1 minus 2 minus 3 and so on, and out of that you simply take whatever is there from 0 to n equal to 5, so 0 to 4. This would be the x1 of n is this, okay, this otherwise the original one would be x1 tilde of n. If you take this, this would give you x1 of n. So that's, again, you can see 4 5 1 2 3, okay, 4 5 1 2 3 here, this one, okay, here this would give you 4 5 1 2 3 is your answer here. Similarly 4 5 1 2 3 here, okay, and this is easiest one. So I would go for, if you ask me, I would go for this, okay, where I would simply move things there and write it there. Okay, that's, we had enough discussion on circular shifting now. Okay, let me move on to, this was the property number 2. Let me move on to property number 3. You could already guess that. Now I would like to do a circular shift of DFT. Okay, that's what I would like to, in the frequency domain of DFT is what I would like to do. So what is that we are going to say? If for x of n, the DFT is capital X of k, and then if I am shifting this, let's say by x of k minus L, can I write it that way? Because this is only n point DFT, there are only n things, so I should bring it back to 0 to n minus 1. So k minus L modulo n, then what could I expect here? E power, there is a negative sign here, so positive sign would be there, j 2 pi by n point DFT, and what else? L times, okay, L times n into x of n. Okay, that's what I would be getting here. Okay, this proof is very straightforward. We have done enough things. I leave it to you. Then the next duality property here, just like we had duality property in case of DFS, very similar lines. If for x of n, the DFT is x of k, okay, and then if I take that with just simply changing the name to n, the DFT would be similar to that, multiplied by n. There we have seen x of, there we have seen minus k. This, as I mentioned, you take modulo n because you are doing all manipulations based on single period of that signal. So this is minus k modulo n. That's all. So before I move further, let me just show you one example for this and then go ahead with this. I should be having somewhere, just a minute, give me a minute. Yes, let me go here. Yeah, this example. Okay, suppose this is what has been given to you. This is your, hope the pen is on, right? This is your x of n. Okay, for you, let's say you are given that this is the real part of it, of x of k. You have computed the DFT of it, and then the imaginary part of your, that assume that it's a complex number. Okay, now what you got there as imaginary part of your DFT, okay, imaginary part of x of k is this. Now suppose I give you, now I give you that this, instead of x of k, I call this as n here, and this is real part of, if I, that's what has been given. Now if this happens to be the real part of x of n, and this happens to be imaginary part of x of n, what is the frequency DFT of it? That's the question. Okay, so this is your real part, imaginary part. You could see there is a multiplication by n, correct? So here there is 1 here, so this is what you need to manipulate now to get here. One thing, you multiply by factor n, right? So the magnitudes, your n is a 10, yeah, this n equal to 10 here, you could notice, assume that this is a 10 point DFT you are computing, right? Okay, and so that means now you multiply it with 10, okay, the whole magnitudes, and then you flip it. Okay, flip it in the way minus k modulo n. Okay, so this, instead of n you consider it k modulo n, so that's 0 will be at anyway 0, 1 would go to minus 1, minus 1 modulo 10, so that's 10 minus 1, 9, so that would come here, then which is there at 1, okay, that has been now dealt with. Now 2 would go to minus 2 modulo n, right, that would come here, then the next one would come here, which is at 4 would come here. So you should be able to solve such problems where you can make use of the duality property. Okay, let me come back from here to our next property, which is a very important property. Okay, this is what we would be continuing in our next video lecture as well, in a slightly more detailed thing. Okay, circular convolution. Yet another convolution you are looking at here. What were the other two we have already discussed? One is linear convolution, another was periodic convolution for DFS, and when it comes to DFT, the kind of convolution you get here is going to be referred to as circular convolution. So here again you assume that for x1 of n, the DFT is x1 of k, and x2 of n, the DFT is x2 of k. Now the question is, suppose if I multiply, this is how we were doing right earlier. So if I multiply here both, let's call this as the result be x3 of n. What would be that? That's the question. Okay, and this in fact the result would be equivalent to, you could already make some guess here, not at all difficult. You interpret it in terms of periodic convolution. Okay, I am doing the same thing here. Hope you all remember the formula for it. If not, refer back to the previous lectures. If over one period will be there, and the first one you just change the variable, and then x2 of, do you remember there what you get for a periodic convolution? N minus m. Now you being treating the whole thing with just one period, you take n minus m modulo n to bring it back to 0 to n minus 1 periodicity. So this is what the definition of circular convolution. So this, for example, x1 of n, it's again, you in this circular convolution you need to mention the with what point df convolution it is. So this is n point circular convolution. So within the circle you write capital N, that means it's a circular convolution, and it's an n point circular convolution. So this is DFT. Okay, and this is the definition. This is referred to as circular. This is n point. This is nothing but n point circular convolution. So this is the third type of convolution you have been coming across in the course of DSP, right? So again I repeat here, had it been a periodic convolution, you simply had n minus m. This being circular convolution, you have n minus m modulo n. Okay, that's all. So let's now solve few examples on circular convolution, right? So this, for example, we had solved one example here, we have seen another example there. So this would be example, let's write it as an example 2 itself here. Okay, so next example 2. Okay, now let's see circular convolution with a shifted impulse is what we are going to see here. We have seen it for periodic already in exercises there. Now I will do it here. I will solve for one and give you another as circular convolution with shifted impulse sequence. Okay, that's what I would like to see here. Okay, so let's call this x1 of n as delta of n minus 2. How does it look like then? This is my n, 0, 1, 2. Okay, so here delta of n minus 2 is, here I have 1, the rest are of course all zeros. This is my x1 of n. Okay, and let x2 of n, let me take something for x2 of n. For example, let me take 5, 4, 3, 2, 1. Okay, 5, 4, 3, 2, 1. So this 0, 1, 2, 3, 4. So this n1 equal to it could be anything somewhere 3, starting from 3 here, and this could this length, let me call this as L1, this length is 3, non-zero length, okay, this is non-zero length is 5. Okay, now assume that the question is compute, as I mentioned, you need to mention the number of points you need to use. So let's say 6 point, okay, circular convolution. That's the question, circular convolution, 6 point circular convolution. Okay, let's work it out. You could do it in different ways. As I mentioned for circular shifting, you could do it in different ways. Okay, and let me do it in one way at least here, and the rest I would leave it to you. So you could already make a guess here from your previous experience. This would in fact would bring a shift. So before that, you pay attention here. This is a 6 point DFT. Okay, so what you should do is you should create a sequence. So x1 of n is equal to, so make the periodicity to be 6 here, 1 0 1 2 3 4 5. I have it 2 1, that was my x1 of n. Let me draw x2 of n again. This was x1 of n, this being n, this is n, x2 of n, for example, this was 5 4 3 2 1, 5 4 3 2 1, okay, 0 1 2 3 4. This is of length 5, but I want 6 point. So assume that this I have additionally 0. So you make this length to be 6, this also to be length to be 6. Okay, the conventional mode of doing this I would leave it to you, but this being a delayed impulse, I am tempted to do it in shifting using the shifting process, shifting property. So when I convolve it, it gets shifted by a value of 2 here. So again, I leave it to you. You could do it in all alternative ways I was discussing for circular shifting anyways. So this would be shifted by a factor of 2, okay, that to the right, isn't it not? So 0 1 2 3 4 5 6 7, okay, should be good enough. Okay, whole thing getting shifted by 2 there. So instead of starting at 0, this would start here. So that's 5 4 3 2 1 0. Now this is of length 6 only, length is 6. So till here this is fine, but this cannot be there here, right? And this is what you move it here, okay, that would make it, for example, this is 1 0, okay, that's the result you would be. So then you just keep from 0 to 5. Okay, so that means the answer would be 1 0, then 2 1 point, okay, something like 5. Okay, I'm not following the scale here, pardon me for that. This is 1 0 5 4 3 2, 5 4 3 2, okay, 0 1 2 3 4 5. That's what you would get as x3 of n, which is equal to x1 of n with n point convolution with x2 of n, where n equal to 6. Okay, hope it's clear to you. Again, you do it in various ways for yourself. I leave that part to you. But I would just give you one exercise here with varying exercise 1, right? For the above, x1 of n and x2 of n, okay, compute compute x1 of n circular convolution, n point circular convolution of with x2 of n for capital N equal to 7. And just I have one more extension here. Compare this result with x1 of n convolved linearly with x2 of n. Check if there is any relationship here that's existing. You draw it and check it out. Okay, that's all for this this one. Let me solve one more example now. Okay, next example 3. This would be the last example I would be solving for this one. Okay, now let's assume I have a rect function. Okay, for the sake of drawing, let me take 6 here, 0, 1, 2, 3, 4, 5, 6. Okay, all with values of 1. Zero, 1, 2, 3, 4, 5. Everything is with value 1. Okay, this is x1 of n as well as x2 of n. Okay, so essentially all I am saying here is x1 of n is equivalent to, this is x1 of n, that's also is equivalent to x2 of n. This is my n. Now what I want you to do is let me write the expression. For example, let x1 of n is equal to x2 of n, that's equal to 1 for 0 less than or equal to n less than or equal to L minus 1, where L is the length of the signal. In this case, for whatever I have drawn, L equal to 6. Okay, 0 otherwise. Okay, now what I would want you to do is compute for example for compute x1 of n point DFT with x2 of n. Okay, for n equal to L. Okay, and what I would also, let's call this as this whole thing as equivalent to x3 of n. So also compute, so I want you to also compute x3 of k. Okay, that's what we will do here. Pay attention here, this is a very useful example. First of all, what do you get for x1 of k? X1 of k, what's the expression for it? This we have already solved it. So you are varying n from 0 to L minus 1. Okay, and its value during that is 1. Its value is 1 multiplied with e power minus j 2 pi by capital N equal to L you are doing. So let me just directly write in that place L times k times n. Okay, this you are already familiar with this expression. You come across that e power minus j 2 pi by L times k times n. This n varying from 0 to L minus 1, in the denominator you have L. So this expression is, you refer back to the DFS of impulse train there. Okay, and then you would come across this. Okay, and what would be that? Well, only at k equal to 0 you are making L summations here. Okay, and of course our L equal to here, L equal to n here. Okay, I could have even written in place of L there n, so I could either write here n or of course L, anything is fine for k equal to 0, and this is 0 otherwise. Okay, this is nothing but the as I mentioned impulse, so that's the basically you have all the signal DC component is there, okay, inverse DFS of 1, okay, impulse train, you look at the DFS and then look at the inverse DFS of it, okay, then you would come across this expression. Essentially you have only DC component in other words, so that's why at k equal to 0 only you would be getting that expression, right? And anyway, this will be also equivalent to x2 of k, both are same. And let me first compute x3 of k directly. Can I compute it from x1 and x2? Of course, yes, that would be equivalent to x1 of k multiplied with x2 of k. Okay, so can you guess what would be that value? N square. For k equal to 0, we are multiplying it, okay, and 0 otherwise. This is your x3 of k. Can't we not compute the inverse DFT of it? Can you make any guess here? What would be the inverse DFT of it from what we computed already here? Make use of the property of scaling here. If you had all ones, you got here the DFT as capital N. Okay, see at k equal to 0 and 0 otherwise. Look at here, all that this DFT versus x1 of k or x2 of k, all the difference that is there is, this is getting multiplied by n. So essentially if you multiply your on the time domain also, if you simply multiply instead of 1 you had capital N, you would be getting here n square. So I could right away by inference, I could write here that my x3 of n would be equivalent to capital N for 0 less than or equal to small n less than or equal to L minus 1, 0 otherwise. Okay, so therefore for capital N, for n, if you are taking n point DFT, you are computing it, and that n is equal to the length of each signal, then your x1 of n, the endpoint convolution, circular convolution of it with x2 of n would give you n from 0 less than or equal to n. I am repeating the same expression, that's all. So 0 otherwise. So all I have here is, in this case, if I just write here, what do I get? Just simply having all the values, okay, 0, 1, 2, 3, 4, 5 here, n. This would be my x3 of n. Can you make that inference from directly calculating the circular convolution also? Not at all difficult. So you what was happening here? You had 0, 3, 4, 5. What was my n value here? N value was 6, right? I have 5. So 0, 1, 2, 3, 4, 5, 6. Okay. So for convolution, this assume that this is my x1 of m, then x2 of minus m. How do I get that? x2 of minus m modulo n. So while you are doing that, you could notice here this is 0, 1, 2, 3, 4, 5. Okay, so 0 would remain, minus of 0 would remain same. So at 0 I have 1. Okay, and x2, so where will this go now? This would go to minus 1 modulo 6. So 6 minus 1, that would give me this 5. Okay, the next 2 would come to this. Okay, and suppose 1 minus m if I am doing it, how could you think of that? 0, 1, 2, 3, 4, 5. If I am doing x, so by the way, before doing that, so to compute its value at 0, okay, at n equal to 0, I need to multiply the corresponding things and add them up. You could see here everywhere I have a summation of multiplication would result in 1. There are 5 such values, so that would give me, sorry, there are 6 such values, so that would give me 6 there. That's why you are getting n. And what would be, for example, if I am doing 1 minus m, you shift whole thing by 1, that's equivalent to having the not having this value. So since you are shifting, the whole thing would start here at 6, you have 1, and then you move it again, so you would end up getting the same sequence once you do that. Okay, so all these values would be 1 again. Okay, so that's why everywhere you would get n value. Okay, 1 2 3 4 5. Hope that's clear to you. Okay, with this I'll give you one more exercise. You please do solve this out. That's very much required, will be very helpful for the understanding the continuations of these things, okay, later. So this I think is second exercise, if I am not wrong. Yes, so the same problem, you take the same x1 of n and x2 of n, but now you compute the x1 of n point circular convolution of x2 of n for n equal to 2l, twice the length of your signal is what you are taking there. Okay, and then you also draw the results. Okay, let me call this as x3 of n. Okay, so draw the results, all those draw the results for l equal to 6. Okay, and also you derive, so let me compute this, let's call this as x3 of k, x3 of n, this is the, let me call it as x3 of n. So now derive the analytical expression for DFT of x3 of n. So that's what I would call it as x3 of k. Okay, and then also you do one more thing, you compute the linear convolution of x1 of n with x2 of n. Okay, and then you compare this result and compare the result with the result from circular convolution, with the result from circular convolution. Okay, and you would notice here once you solve it, in fact this linear convolution would be same as circular convolution. Okay, don't consider this as an accident, this happened accidentally. This would be, in fact, is true for under certain conditions, this is what would happen. So I also want you to contemplate on why you are getting the linear convolution, when is that the circular convolution and linear convolution are becoming equal, and why they are getting equal. So that would be the content for the next video lecture. But meanwhile, I would ask you to contemplate on this. Okay, circular convolution becoming equivalent to the linear convolution. Again, there are few more properties I have not done myself. I won't be going through this rest of these properties. I would ask you to go through them yourself, not very difficult to follow. And again, I could ask you questions in the exam from any of those properties. Okay, so that's all. So let me stop here. Just a minute. Discard the changes. Okay, let me come back here to the presentation mode. Okay, so that's all for the properties of DFT. To summarize, the most important thing that you would be studying here is the circular convolution, which is equivalent if you are multiplying the DFTs of two sequences, endpoint DFTs of two sequences. What you would get, you would be referring to that as endpoint circular convolution, and you should be able to perform the circular convolution given a couple of things. And again, circular shift is another thing you are studying, where you want to do manipulations based on a single period of the signal. Okay, given, say, as if you are treating with one period of the signal, that's equivalent to it. So go through them carefully, And in the next video lecture we would be discussing about performing linear convolution through circular convolution, and of course why we want to perform that, and many other things we'll be discussing there. Okay, thanks for watching. That's all for this. Take care. See you in the next video lecture.